Okay, so I believe we are recording right now. So this is the ghost lecture where apparently we couldn't get things to work, so I'm going to do this in post. Hopefully some of you guys email message and are able to join me midway. But I want to continue on with something that we're going to be calling solution stoichiometry. It's exactly the same as what we have been doing in the past. But we're going to start and end at different places. Now, specifically, remember I said with mass to mole to mole to mass, it was always going to be something to mole to something for these conversions. Now, as we start moving on to that, I do need to define something here as one of the somethings, and that is we're going to talk about molarity. Now, molarity is one of those things that we have to define because it's going to make our life easier. Just like grams per mole made our lives easier, so will this. Molarity is also called concentration or strength. So you will hear these terms used often interchangeably. We'll say, what is the molarity of that acid? Or we'll say, how strong is that acid? Or how concentrated is that saltwater solution? All of these are molarity. And molarity is given a capital, well, it's technically a script M, or an italic M, is defined as moles of solute per liter of solution. So molarity is moles over liters. And it's a way for us to take into account the amount of stuff inside of a liquid volume. And that's how most of our experiments go. We go in there, we've done enough experiments already where we went drop, 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 and drop, 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 and we looked for a cloudy or a color change or something. Basically, we had a certain number of things, right? So if we look at this, it's all about the number of things. So this is just the stuff, the amount of stuff. In the solution. Now, we're going to do moles because we have balanced equations, and those balanced equations are on molar ratios, okay? Now, when we look at this M right here, okay, what we're really asking ourselves is how do we implement that? And so if I say we have something like a 2 molar HCl solution, which means the molarity of it is 2 molar. You notice there's a slight difference in how I say it. 2 molar solution, or its molarity is 2 molar. What this really means is that there's 2 moles of HCl per liter of HCl solution. Eventually, I'll stop using this solution on the bottom, and we'll say 2 moles of HCl per liter of HCl. The implication is that it is a solution. So whenever, and let me be very clear, it is always on a 1 liter situation. We just usually leave the the 1 off. So this molarity or concentration or strength is going to be very advantageous to us because it essentially removes a step from conversions when we're going from one thing to another. Now, let's take a look at a couple of examples of just straight up conversions or figuring something out, and then we'll move to what I like to call the molarity to mole to you name it type thing. So let's take a look at an example how we might use this. For example, 20 grams of sodium hydroxide is dissolved in 500 mils of solution. What is the molarity? Meaning how concentrated is this solution, or what is the molarity? All right. Again, trying to make sure that you guys realize that when we say or concentration or strength, we are talking about the same thing. Okay, so this is a conversion just like we normally have. So what we want is we want the molarities or moles of NaOH per liter of NaOH. We always write down where we're going. Now, you guys recall, I keep saying these questions over and over and over. And I ask myself, is there anything up there that looks like moles? Anything up there that looks like moles in our prompt? And hopefully you guys remember that mass and mole are exactly the same thing. We just have to go to the periodic table. So let's go ahead and start with those 20 grams. So we'll say 20 grams of NaOH. And let's just convert those to moles. Now I went to the periodic table and I know that it's 40.00 grams of sodium hydroxide is 1 mole of sodium hydroxide. Again, adding up the parts to make the whole. And because I went to the periodic table, it's only 1 mole. It means our grams have canceled. Now we have the moles of sodium hydroxide that we want. Now we just need the liters, and hopefully you guys can see I got some milliliters here and liters here. I just have to put them where they need to go. And since liters is on the bottom, I'm going to put that half a liter of sodium hydroxide there on the bottom. I don't need anything up there, so I'll just make myself happy. Now, if you do that, you should end up with a 1 molar solution, I believe. Let me get my calculator, just double check it, or just trust my notes and hopefully somebody gave me yeah, that's right. Now, of course, you can actually rewrite this if you wanted. You can leave it as moles over liter. I'm totally fine with that. Or you could say it's a 1 molar sodium hydroxide. So what we've done here is we've solute this 20 grams of sodium hydroxide right up here, and we're going to put that into a half liter solution or 500 mils. How strong is it going to be now? And we find out we've just made a 1 molar solution. So 1 mole for every liter of stuff. So we know how much is there. Let's do another example here. So how much NaCl do we need to make 250 mils of 0.15 molar NaCl? Now I'm going to remind us about a couple of things as we do this problem. Remember, the Wayback Machine, of in mathematics means multiply, so you're probably going to put those two things together. We should also remind ourselves, and I love doing this every time, that big M means moles per liter. I always remind myself that, because hopefully you guys see that when I ask for this how much up here, I'm actually asking for the grams. It is salt, so we're expecting it to be a solid, and it should be a mass. So looking at that, we have some clues as to how we're supposed to do this problem. The how much, we want to figure out the grams. How are we going to make it? We need 250 mils of this 0.15 molar. Those moles and those grams are where we're going to be starting. So over here, we need grams of NaCl. And I notice here that my moles and my grams, those are the same thing. So I'm going to start with 0.15 moles of NaCl per liter of NaCl. And we can go about this one of two ways. I can either get rid of my liters first, or I can convert those moles to grams first. It doesn't matter. I'm going to go ahead and get rid of my liters because math is telling me, why don't I go ahead and multiply them? So hopefully it's not too much of a stretch to know that I have 0.25 liters of NaCl. Since that's the only thing I have to do, it's going to make me happy. Now all I have to do is get this moles to mass. And again, the periodic table is our friend. If we go look it up, it should be 58.44 grams of NaCl. And since we go to the periodic table, it's 1 mole of NaCl. We have our grams like we want. And if we do that, we should get 2.19 grams of NaCl is what we need. I can write a 2. Okay. Now, this is pretty straightforward, hopefully, and no one is freaking out. Really what this is it's all about chasing the units, figuring out what you need to find, and look in the prompt to see is there anything that can already get me where I'm going. In the one we just did, we were looking for the how much, the grams. We go back up, this how much, grams. We go back into that prompt and say, is there anything up here that looks like grams? Meaning, can we easily do that? We see the molarity. We reminded ourselves that molarity is moles over liters, and we know that moles are grams and grams are moles. It's just a conversion from the periodic table. Once you remember that, we are able to start getting rid of stuff that we don't need, namely these liters right here. We need to cancel them out. So again, the problem is sort of telling us what we need to do. We need to multiply those things. We can get rid of one of the sets of units and then convert the last set. It's one thing to do these, it's another to do the next awesome. And this is where we get into what is called the solution stoichiometry. Solution stoichiometry. And again, if you remember from class earlier, I said stoichiometry was really just the Greek for saying counting of the atoms. So this is nothing more than keeping track of your stuff. And we are going to do that with an example. I'm going to do one example. There's going to be plenty as we go along into the neutralization. There's plenty in your homework and in your lab manuals for you guys to try. And of course, we can do some more when we come back at the next class period if you guys still have some problems with this. But I'm going to jump into a problem that should show us many different ways that we can actually go about this problem, solving any of these. So this example is going to be, we're just going to learn by example, because that's how we do it in this class. I'm going to say 100 milliliters of 0.1 molar magnesium bromide reacts with 18.2 milliliters of silver nitrate. What is the concentration? What is the concentration of the AgNO3? How much product is made? So we have 100 mils of 0.1 molar magnesium bromide. We're going to react it with just a small amount of silver nitrate. And I want to know how concentrated was that silver nitrate. We're assuming there's no limiting reactant here. They're just going to do what they do. And I'm going to ask how much product is made. Well, in order to do this, we're going to have to start digging through all of our toolboxes. So we're going to dig way deep and say, well, I need to know what's going on in the first place. So I need to know the magnesium bromide, which is aqueous because of the bromide, is going to react with silver nitrate, which we know is aqueous because all nitrates are soluble. And hopefully you guys recognize that this is the good old-fashioned double replacement. And so we'd end up with MgNO3 which has to be aqueous because all nitrates are soluble, and some silver bromide. And so if one is soluble, the other is not. And then we'll go ahead and we will balance it out. Now, as we have that equation, now we know what is going on. And so now we can start to look. What is the concentration of AgNO3? We know we're looking for a concentration because it is a liquid. How much product? We're asking for that thing we actually made. If it's still swimming around at the end of the day, you didn't actually make it. They're still just swimming around. The fact that silver bromide is a solid, that is our product right there. So we have two problems to do here. So let's take a look. The concentration of AgNO3, of course, if we see that word concentration, we should be thinking molarity. So coming down here, let's do the first one. We want the moles of AgNO3 per liter of AgNO3. That's what we're looking for in the first place. And again, we should always be reminding ourselves that this big M is moles per liter. Now, I always like taking my problem and dissecting it down to figure out what I need to do. When I'm doing these, I always expand things out. I take that big M and make it a moles over liters. If I see other words in there that may or may not have synonyms, again, concentration here, molarity, looking for the same thing here. I need to know how much product is made. Well, look down here at my equation. Oh, there it is. There's a solid. That must be the thing that I made. I always really think about this problem before I just dive in and start punching stuff on my calculator, because it really is important to set this problem up correctly. So we are looking for this moles of silver nitrate per liter of silver nitrate. Let me make sure that looks like an L instead of a 2. Oops. And let's make that purple. And so when I look at this moles over liters for the silver nitrate right here, I say, hey, is there anything up there that looks like moles per liter in my problem? And right there, my MgBr2 has a molarity. Hey, it looks like we got somebody. Go, feel free to unmic if you want. So if I see something that I want to get, and there's something already there that I can use, I'm gonna go ahead and do that. So just like if you want a mass, you're gonna start with that mass. If you want a molarity, you almost always wanna start with that molarity. So I'm gonna start with the 0.1 moles of MgBr2 per liter of MgBr2. And we're gonna remind ourselves, math is telling us what to do. Math is telling us to multiply those so we can get rid of our volume. So remember, I said from here on out, the problems are essentially always going to be something to mole to something. So I can just go ahead with my boxes. I can say something to mole to something. Looks just like a mass to mole to mass calculation. These will all follow the same sort of pattern. All right, the mathematics of tells me to go ahead and multiply that by my 0.1 liters of MgBr2. Notice that I've now taken my molarity and turned it just into moles. So I went from molarity to mole. Now I'm going to go from mole to mole. And that's where the balanced equation comes in. We look up here, we have 1 MgBr2 to 1 silver nitrate. So we have 1 mole of MgBr2 to every 2 moles AgNO3. And so now we've gone from molarity to mole. Now, right now, we have our moles where we want them. We just now need the volume. And so I asked myself, is there anything up there that looks like the volume of silver nitrate? And lo and behold, it's right here. We got it right here at the 18.2 mils. Since I need that on the bottom, I'm just going to put it on the bottom. So that's 0.0182 liters of silver nitrate. Again, if you don't need something there, just be happy you don't have to put something there. And in the end, we have moles per liter. Again, we went from something to mole to something. In this case, molarity. Getting rid of our volumes here leaves me at moles, then to moles. And at the end of it, we have moles over liters for our molarity. If you punch those numbers, you should get 1.10 moles per liter. Or if you wanted to, you could say 1.10 molar AgNO3. Again, okay if you just left it as moles over liters. They're the same, it's just the big M for molarity is cleaner. Okay, so we have done one of these problems right now. We've already gotten rid of the what is the concentration of our silver nitrate. Now we're going to figure out the how much of the product is made. Now, hopefully you guys see that since this is a solid, we're looking for a mass. All right, so when we look at that and we see that solid, that means we're looking for the grams. That's the thing we made. So again, just like every other problem, we're going to come over here and we're just going to say, look, we're looking for the grams of AgBr. So we have to ask ourselves, is there anything up there that looks like grams? Hopefully, you guys said, yeah, I see up there in that prompt. Go back up there in that prompt. I see that there is a molarity, and in there, hidden in there, are some moles, and moles are grams. Now, those are currently the moles of magnesium bromide and not silver bromide, but we should be able to work with that. So let's take a look. Come back over here. And you'll notice, by the way, 0.1 moles of MgBr2 per liter of MgBr2. Hopefully you notice, just like with our mass to mole to mass calculations, if I'm starting at the same place, it should be no surprise that no matter where I'm going, if I know the amount of one thing, I know the amount of all. So we are going to start in the same spot there with the MgBr2. In the top one, we said that it was molarity to mole to mole to molarity. This one is still going to be the same mantra. We're just going to end in a different place. So this will be a molarity to mole to mass now. So again, something to moles to something else. The mantra is the same. You just have to know where you're beginning and where you are ending. And so all we have to do now is play with our units. And again, this problem is telling us what to do. 100 mils of the 0.1. We are going to be multiplying those things. So come back down here. And again, take a look. 0.1 liters of MgBr2. Our first steps shouldn't be any different because we're starting at the same place. It looks exactly like the problem above. The only thing now it's going to be is we're going to go to a different endpoint. And so we know that we've just gotten rid of our liters of mgbr2. We need to get rid of the moles. And that's now going to be via the equation. So go back up there and we see 1 mgbr2 to 2 silver bromides. So I'll say 1 mole mgbr2 to 2 moles of AgBr. We don't want moles, we want grams, but at this point, we are pros at this. We go to the periodic table. Silver is 107.9. Bromide is 79.9. So 187.8. This would be 187.8 grams of AgBr. And since we went to the periodic table, it's per 1 mole. Once again, we have what we want. If you go ahead and punch that in your calculator, you should get 3.76 grams of AgBr. Now, when we do these problems, again, it should be noted that there really is nothing new about these. It's always something to mole to something. You just have to be very careful and very fastidious about going through this and labeling, okay, what am I doing? I got an oven here. I'm probably going to multiply. This big M means moles over liters. That way I can look for the moles, or I can look for a volume or something. What does it mean to be concentration? Oh, I'm looking for molarity. What do you mean how much? Oh, it's a solid. Okay, I'm looking for a mass. All of these little clues in the setting up early is really what you want to do, because it's going to make your life a whole lot easier when you get down to this stage, which is still pretty easy. It's the stuff we've been doing for a couple of weeks now. All we're doing is beginning and ending in a slightly different place. It's okay. Now, we'll be doing a lot of these. We'll be doing a few more next class period when we look at neutralization reactions. And of course, the homework and the lab problems have a ton of these. So by all means, get some practice in, because we all know that it's the practice that's going to make us good at it. Now, we talked about things being concentrated or how strong they are. Dilution is another thing we need to talk about, and it really has to do with this concentration or molarity or strength. Whenever you have something that is really strong, you might want to sort of, well, I hate to say it, dilute it down. It's really hard to not talk about this definition without using the word. But really, let's face it, what does dilution mean? It means to, quote, water it down. As far as we're concerned for this class, all we care about is watering something down. You can dilute with other things, but we're only going to use water here. And really what it means is make something less concentrated. Make something less concentrated. All right, you might want to think about diluting frozen orange juice. If you don't know what that is, you will pretty soon with all this lockdown. You're going to be buying a bunch of frozen juice so you can just have it. And you know, for anybody who's made soup from a can, if you don't want it as watery, you just don't add as much water. We've diluted things over and over throughout our lives. But let's talk about what that means. When we're making something less concentrated, what are we actually really caring about? The something here is we want to make the solute less concentrated. So when we're adding more water, we're actually spreading out that solute. We're trying to make its presence in the solution more dilute. Now, since it is about the solute and a concentration, right, we're going to be talking about molarity. And there's one very easy thing to do here, and that's M1V1 equals M2V2. And hopefully you guys have already made the intuition that the M is molarity. V, intuition, is probably going to tell you that's volume. And this 1 and 2 is really just a way of keeping track of the fact that this might be the concentrated side and this might be the dilute side. It's really just a way of saying before and after, initial and final. So it's just a way of keeping track of which molarity and which volume go with which side. I'm going to do one example because these really are just plug and chug situations. I'll do one example, and I'm pretty sure you guys will get it. This will be how much concentrated 12 molar HCl do I need to make 60 milliliters of 0.1 molar HCl. Okay. Now, again, looking at the problem, trying to figure out what this problem is. You know, when we get to this exam, a lot of people rush into making the boxes and go, go, go. While that works for a lot of these problems, you have to be careful. This problem is not that. This is a dilution problem, and there's a few things to tell you that it is a dilution problem. Sometimes you will have the word concentrated or diluted in the prompt, but even more telling is the fact that there is no reaction. We're going from HCl to HCl. There's no reaction here. We're basically just taking it from a big number to a small number. That's it. Oh, and look at our other hint here. What does of mean? Times. So it's already telling us, take that 60 and that 0.1, those two things are together. I don't care which side you put it on, the math will work. I'm going to go ahead and put it on the dilute side just because we've sort of denoted that. So I'm going to say I have 12 molar HCl, and you know what, since we don't have to worry about that, we'll just say 12 molar times, I don't know what that volume is going to be yet, is going to be equal to the 0.1 molar times the 60 mils. If you go ahead and do that, you'll find out the V1 is equal to a half mil, 12 molar, and you will now dilute with water until it is 60 mils big. Now, some of you may be astute enough to say, wait a minute, if molarity is moles per liter, why are you putting 60 milliliters? It's okay, because what's going to end up happening here is it's not about the volume, it's about having those molarities cancel out when you do the math. So no matter what volumes you use, I don't care if you use ounces, I don't care if you use barrels, it will all come out in the end. Now, at this point, that's as hard as these get, so that's the only example I'm going to do for dilutions. So hopefully that's some easy money on the exam. Okay. So we've introduced molarity, concentration, strength, the amount of solute, moles, over the volume of solution, liters. It's a way for us to take all the chemistries that we would normally do on the benchtop, where we're just drip, 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 and drip, 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 and oh, look, it got cloudy or something like that. all of the stuff that we're doing to the end of the semester will involve watery-based chemistries, because that's usually how we want things to be. It's easy to transport, it's easy to take care of. And so we have now introduced these so-called solution stoichiometries, where you can start with a molarity and end with a molarity. You can start with a molarity and end in a mass. I'll tell you right now, you could start with a molarity and end in a volume. And you can do all of those in reverse. So these problems, again, are not difficult as long as you slowly and methodically label what you are looking for in the problems and just work yourself through the units. Chase the units and you can't go wrong. Oh, look, I forgot to do a happy face. Again, try some problems at home, bring them to the next class period. So if you have questions, we can go over them. All right. Oh, we're getting close to the end. We need to start talking about acids and bases. Okay. Now, most of us have an idea of what an acid is. But the base may be a little more unfamiliar, and I'll talk about that here in just a second. First thing I want to do is define what is an acid. Now, we kind of already know this from our nomenclature. It turns out while we knew some things were acidic, we had no definition of it until this guy came along named Arrhenius. Now, the Arrhenius acids, I named Arrhenius, basically figured out that the bark of a tree would turn a certain color if it were in the presence of an acid or something that was a base. The Arrhenius acid, he finds out, will give H pluses in solution. Now, of course, we knew that, right? We knew that because what's our acids? HCl or H2SO4. We knew that those were acids because acids start with H. So it should be no surprise that when Arrhenius figured it out, it was because it gave us H's. Now, of course, some of this you may be asking, is it a chicken and the egg thing? Well, they knew what acids were, but they needed to know their composition. Once they figured out there were H's in there, they figured out the rest of it. So it all sort of comes together at once, if you will. Now, if you remember your types of reactions, then it should be no surprise that the Arrhenius base gives us the other half. This will give OH minus in solution. So things like sodium hydroxide, okay? Now, of course, I mean, neutralization, what do we make? We make water, or HOH. So again, these two definitions shouldn't be any surprise to us, but now it might make sense as to why they did what they did in the reactions for neutralization. Now, when we talk about the acids and bases, one thing to be all like super chemical on it and formal, but I told you, as I'll tell you again and again, I'm not going to tell you anything that you don't already know. I'm just going to tell you why. So let's talk about some common acids. Ooh. I'll do common acids. Now, normally at this stage, I'd make you guys start shouting out all sorts of acids and what do you think here?
Lemon.
And I usually get things like, well, in lab, we've seen good old-fashioned HCl, and of course, you just wrote up there H2SO4, duh. But if you think about other acids in your life, you should have acetic acid. You should have phosphoric acid. This is in your sodas. It's also used for pickling and preserving. If you're really cool, you might remember citric acid, right? Or lactic acid. If you work out a lot, you're like, oh, that lactic acid burn, right?
Stomach acid.
Maybe your good fashion vitamin C, which is ascorbic acid. Right? We can keep going. We know tons of these. Now, if you look at what all of these might have in common, you'll note that they are sour or tart to the taste. So you get a little acetic acid or some vitamin C or a lemon. It's got that sourness. It's got that tartness to it. And this was actually the original way they figured this stuff out, is they would taste it. The early scientists were babies. They're putting everything in their mouths. And what they found is that the things that were acidic had that sour or tartness to them. Now, it turns out human beings actually like that. So most of the things that we like to eat, which is to keep us alive or otherwise make our tummies feel good or our mouths go, yay, yummy, we'll end up with acidicness to it. Human beings love acids. So normally we can label a ton of these guys. These guys are sour or tart. The bases might be a little harder. So common bases. Now I'm going to say that it's harder, but I'm going to give you a bunch just because if I don't, we will not get anywhere. Now bases, common ones that you would be aware of in your life would be something like ammonia. Good old NH3, or baking soda. NaHCO3, or good old Drano, which is just sodium hydroxide, or lime. For anybody who works in construction, this is your concrete. That is calcium hydroxide. Now, of course, right here you can see at least our last two examples have the OH on them. That's to match up with the Arrhenius definition. The first two might be a little hard to see why they're going to be called a base. I'll show you that in just a moment. Now, the thing here is, if you've ever worked with ammonia in any concentrated amount, or baking soda, or man, if you got lime on your hands, you would notice that each of these has something to it. Bases are slippery. They're very slippery. So when I went over to Mono Lake and I was going to hike out to the little tufas out there and stuff, I was like, oh, you know what I'll do? I know that the lake is basic. This will be cool. I'm going to touch the water. And I pulled it out because the pH of that thing is 10. It's pretty basic. And all of a sudden I was like, oh, that's right. I rubbed my fingers together and they were slippery. And I was like, man, it's a half mile back to wash my hands. And I can't wash it in this water because it just makes it worse. So I had to like walk a half mile to wash my hands off because I just didn't want the slipperiness on it. So if you ever get Drano or lime or any of that on your hand, get it off fast. Bases love to stick to our hands and they're slowly saponifying them or turning them into soap. That's why they get all slippery. Bases are bad. If you have ever worked with baking soda and you happened to taste it, you'll find out that it is bitter to the taste. So bases are bitter and they're also slippery if they already happen to be in a liquid form. Aside from these common bases that you and I would see on a regular basis, and even some of these normally you wouldn't, unless you worked in concrete, you wouldn't even know about lime. You're not going to be able to find too many basic things that you want to talk about, and mostly because human beings don't like bases. Bases happen to be one of Mother Nature's defense mechanisms because bases love to eat organic material. And so the last thing you want to do is ingest something that's going to be harmful to you. And so we've developed as humans an aversion to anything that's bitter unless you make an acquired taste to it. And again, if you get it on you and it's slippery, it's probably not a good thing either. So acids are sour or tart to the taste. Bases are bitter, and they happen to be slippery if you actually get them on it or on you. Now, this is just to show you that we know more than we think we do. We know a lot of different acids, and we could keep going on with other acids. There are many of them. For my wine people out there, you got your tartaric and all that. Bases, though, man, that's the short list, because after that, you have to get into some really unique things, because, again, as a rule, we don't like working with them because we can't eat them. I know we bake with baking soda, but that's a different thing. We'll talk about that offline if you want. But none of us goes around drinking Drano and ammonia for fun. We do, however, have phosphoric acid in our sodas. We eat vinegar all the time. Vitamin C, not a drama. Most of you at least have a cursory knowledge of what I'm about to tell you. And that is, we have a pH scale that sort of ranks how acidic or basic something is. And that scale runs from 1 to 14. And notice I put a 7 there in the middle. Everything on the low side here is the acids. Acids are small on the pH scale. Bases are big on the pH scale. Which means, who's this guy right in the middle? Well, we know an acid and a base, what do? They neutralize. So 7 is what we call neutral. So acids are small, bases are big, 7 is neutral. Now, before we actually get into those calculations, what I want to do is continue on with some of these definitions and how we can glean a little bit of information from these definitions. So let's go back and look at the Arrhenius acids and what they can tell us. So let's look at the Arrhenius acids. As we said before, these guys will give H pluses. Now, if we look at HCl, when it goes into solution, it should break up and give us H's and Cl minuses. This is what is making the acidic nature of it. But we have a few other acids we could look at, and that is H2SO4 or even H3PO4. And hopefully you can see this cool thing right here. So what's happened here is when it breaks up, it's giving us their H's. So we see the HCl gives us 1, H2SO4 gives us 2, H3PO4 gives us 3. Now, we need to keep that in mind when we start doing some calculations a little bit later. It's not that it just gives us H's, but we can actually figure out how many H's. This one right here, the HCl, is what we call a monoprotic, meaning one H. The H2 is a diprotic, meaning because it's 2. And of course, H3PO4 would be a triprotic. So as you go down your career, somebody may call it a mono, di, or triprotic. You just know that it's 1, 2, and 3 H's. Even if you don't know what the acid is, you'll know how many H's it gives you. Now on the bases, it's very similar. So remember the Arrhenius base. These will give OH minuses, and depending on what it is, you will know how many. So again, NaOH and CaOH2 will give us differing amounts of OHs. Na plus and 1 OH, or Ca2 plus and now 2 OHs. So we got 1, we got 2. Just be aware of the stoichiometry. We don't have a mono, di, or whatever for those guys. Usually we just use it for the acids. Now, I do want to point out that I've perhaps done something that is slightly disingenuous for you, and that is I have made an implication that is not always true. With this monodiene triprotics, you would think that, man, that phosphoric acid, that's some really strong stuff. It's giving us 3 H's, and HCl is only giving us 1. Well, that's not genuine. HCl is a strong acid, and phosphoric is actually a very weak acid. So while it wants to give us 3, it only kind of wants to. And for more on that, come to Chem 121. But let me talk about what does it mean to be a strong and a weak acid, strong and a weak base. So strong acids. These will give all H pluses, okay? Completely, 100%. There are only 4 of these guys that I expect you to know. There are a few more, but I expect you to know these 4. And they're going to be HCl, H2SO4, HNO3, and HClO4. You'll notice if you think about your solubility rules, sulfates are soluble, all nitrates are soluble, perchlorates are soluble, and of course the chloride. And they're also paired with an H that wants to be soluble. So it's no surprise that those all will go swimming. Now, looking at weak acids, so comparing them to weak acids, these give only some of its H pluses. Now, while the actual equation says, there you go, there are your H's, there's a difference between giving and giving. And so things that are weak acids are things like acetic acid. HC2H3O2, of course, gives us the H plus and the acetate, okay? But only 1% does this. The rest of the time, it's just hanging out as the molecule. Very little actually breaks apart. H3PO4, right? That's a weak acid. Citric acid. All of these are weak. Now, how do we know that? How do we know it is a weak acid? Easy. Would you eat it? That's what you want to ask yourself. Would I put that into my mouth and eat it? Vinegar, yes. Phosphoric acid, of course. Citric acid, I eat it all the time. So if the answer is, yeah, I'd probably eat it in one form or another, it's weak. Otherwise, those 4. But most of the acids out there are actually pretty weak overall. Now, if strong acids give all the H pluses and weak acids don't, we can extrapolate that to the bases. So the same sort of thing, the strong base, these will give all their OH minuses. And there's really only a few strong bases, and that would be something like sodium hydroxide and potassium hydroxide. While there are other basic things that are pretty strong, these are the only 2 I expect you to remember as being strong. The weak bases, right, they do not give all H pluses, or OH minuses. And examples of this would be NH3, NaHCO3, basically anything not NaOH, and KOH. Now again, I'm only going back up to those common ones that we see that I put up here, because bases, these guys, there's not that many of them that we are familiar with, so I'm just going to keep it simple. Okay, so I think I'm going to go ahead and stop it here. No, I'm not. I'm going to go just one little thing more. Because if any of you are a little astute here, you've been looking at some of the things I've been writing, especially when I come up here and say, oh, giving OHs, and you're like, well, where's the OHs there? What? Well, there's where there's another definition we need to worry about, because once people realized what an acid was, what a base was, they started saying, okay, I get that, but if that's the case, then what about this that has no OHs? Why is it acting like a base? And a couple of people got together and figured it out, and their names are Bronsted and Lowry. So Bronsted, Lowry, acids and bases. They said, I like Arrhenius's definition, but we got to go one step further. So for their acid, what they said is it will be a proton donor. Really what they meant is an H+, because if you can imagine, a hydrogen only has a proton and an electron. If it gives away its electron to be an H+, it is technically just a proton floating around. Well, if not A, then B. Instead of donating, the base is going to be this proton acceptor. So it's going to actually take that H+. And you'll find that as we do this, it doesn't violate what Arrhenius said, but it just now expands who can do what. So I'm going to put well, a couple of them up here. And that is, if we have HCl plus NaOH, this is going to make good old-fashioned salt water. Okay, it's going to look like a double replacement, but at the end we make water. Okay, so at the end we make water, so we know it's neutralization. Hopefully it's not too much of a thing to see, oh look, HCl, that is obviously the acid because we call it hydrochloric acid. But moreover, it's that the H is donating to the OH to make our liquid water. So it's going to donate the H+, which means it's the acid. This is accepting, which makes it the base. Now, obvious trivial example is trivial. So let's step it up just a little a notch here, and let's introduce one of those guys that is not intuitive, HCl and ammonia. Now at this point, you're like, wow, that's kind of weird, unless you realize that since you have an acid here, clearly an acid, if it donates to the NH3, you can get NH4 with a positive, and that Cl minus is going to be running around. And so what they've done is this HCl is still donating. Just because we're in a different situation doesn't mean the acid isn't the acid here. So that donate, the H plus, makes it the acid. But now we see that the NH3 is basically accepting it from it, not basically, making it a base. And so even though NH3 does not have an OH to it, it is accepting that proton, and by doing so is acting like a base. And so when it does that, we can actually see that while it doesn't have what Arrhenius would say would define it as a base. This covers that aspect of it insofar as it'll accept the H+, which gives it the basic properties. So I just wanted to put that one down real quick because I've been putting them up here and all these basic things up here, and everyone's been like, oh, wait a minute, I'm uncomfortable. Don't worry, we'll do another one when we come back next week or tomorrow, I guess, and it'll involve this NaHCO3, and I'll show you how that actually is a base. Okay, thus ends the ghost lecture. Thank you for my one ghost who was able to show up. Any burning questions before I go ahead and end it? Ghost?
Nope. I don't think you can hear me.
Uh-oh. Do I not have audio? I can't hear you. Oh, well, I can't hear anything, April, so I don't know why I can't. So either put it in chat real quick or just save it for tomorrow. I don't know. Are we going to save it, April? Huh. I don't know why I didn't hear you. Hopefully I'll fix it by next time. All right, well, thanks for showing up, April. And be sure to ask those questions tomorrow when I think we'll get this going. All right, have a good one.